All right, this is a demonstration of the Fortinet SD-WAN ADVPN. In this setup here, we have our hub, which is our data center, with two separate ISPs. We have a branch office 2 with two separate ISPs, and branch office 3 with two separate ISPs. The assumption here is that ISP 1 is a top tier provider, and ISP 2 is more of a SOHO cable or DSL style backup internet provider. Thus, in this specific scenario, we want to prioritize ISP 1 for all traffic. We do have some hosts. We have a host up in at the hub at the data center of 1.1.1.1, a host at branch 2, 2.2.2.1, and a host at branch 3 of 3.3.3.1. So for the test we're going to be doing, we're going to simulate for test number 1, branch traffic to the hub. And let's do that right now. So from branch 2, if we simply ping the hub, we can see that the traffic is going over the preferred path, which is the low latency path toward the hub. Over here, if we look at our SD-WAN rules, and we look at our rule here, our ADVPN traffic is preferring overlay 1 if we meet SLA. And the SLA is 100.100.100.100, which is a loopback address within the hub. And as long as that is within our SLA, which is 120 milliseconds, we will choose that path. Obviously, we can set jitter thresholds and packet loss thresholds, but for this demonstration, we're just doing latency to keep it easy. So right now, we're taking, if we look at our SD-WAN rules, we are taking the overlay 1 path between branch 2 and the hub. Now, if we were to introduce latency and bring that latency above that threshold, we can see traffic spike up to 332 seconds. If we look at our performance SLA, let's refresh that a little more. We see we are now out of SLA. Since we're out of SLA, the rule kicks in and it flips us over to overlay number 2, which is a slower link as it's a cable modem DSL, and we're down to 22 milliseconds. If we look at our SD-WAN rules up here, we can see that we're out of SLA and the rule pushed us over to overlay 2. So let's normalize that. And what we expect to see is this drop back down to sub 1 millisecond again. If we look at our performance SLAs, we should see this go back into SLA, and we should see the traffic drop as it did. So that satisfies test number 1. Now the next question is with traffic originating, what we just did is originating from the branch up to the hub at the data center. Now, how do we have the simulation going in the opposite direction? How does the hub realize that there's an issue on one of the overlays and switch traffic over? The way that happens is once the branch is out of SLA, it sends a routing tag toward the hub to dirty up that path and come across the other link. So let's do that again. In this case, let's close this out. Let's open up the hub PC, and let's get a ping back toward 2.2.2.2. I'm sorry, 2.2.2.1. As we can see, it's taking the optimal path across WAN 1. Let's come in here and let's dirty that up again. So we immediately see the delay increase. If we look at our overlay, we see we are out of SLA. This triggers a route tag to go up to the hub and tells the hub to come back down the overlay 2, as we see here. Now we're on overlay 2 with the 22 millisecond latency. Let's normalize that. And we should see it flip back. There we are. We're back within SLA, And we should see the path flip back to overlay 1, which is the sub 1 millisecond, which we see here. That satisfies test number 2. Now for test number 3, let's look at the topology here. So test number 3 simulates shortcut pathing. What shortcut pathing is the branch wants to talk to another branch, say from branch 2 to branch 3. The initial packets will go up to the hub. The hub will then send a shortcut offer to branch 2 in order for it to find a direct path to branch number 3. If we didn't do that direct path, we'd have added latency from the traffic basically hairpinning through the hub, coming up to the hub and back down. This is something we can turn on, and this is also something that we can turn off. If you're in an environment that needs a full mesh VPN where all sites can get to all sites, you want that shortcut pathing turned on. If you're in a architecture where the branches do not need to talk to each other and you do not want them to talk to each other, you would only allow traffic from the branch directly to the hub. So let's simulate this. And the way we can see this here is if we look at our IPsec monitor here, we only have 2 VPN tunnels actually built. One to overlay 1 and one to overlay 2. That is across ISP 1 to the hub and across ISP 1 to the ISP number 2 to the hub. There's absolutely no VPN tunnel built between these two. But let's get one built. 3.3.3.1. And you can see the very first packet is 2 milliseconds. The reason is because the packet goes from branch 2 to the hub and then back to branch 3. And during that time, the offer of the shortcut path is built, and we have a direct shortcut path, thus the latency drops. So if we actually refresh our IPsec tunnel list here, you should see the overlay 1_0, which is a direct path to branch number 3. So that's a shortcut path. Now, what happens if we introduce latency here? What we expect to see is that a shortcut tunnel is built across overlay 2. There's our latency. Let's refresh this. We're waiting for the SLA to go out of SLA, and we can see that we're now using overlay number 2. If we refresh our screen, we can see that a overlay 2 shortcut path directly between branch 2 and branch 3 was built right here. Let's remove that and normalize it. We should see our SLA go back into SLA and pass, and we should see that drop back to the shortcut path across overlay number 1. And there we go. So that satisfies test number 3. Now for test number 4, let's simulate an ISP circuit going down. So what we're going to do here is actually break port number 1 on this device. So if we go to the network in our interfaces, and we have WAN 1 port 1, let's go ahead and disable that interface. We lose a few packets as things figure themselves out, and we see that things are converged, and we're now using overlay 2. So let's bring that back. Now to bring it back, it's going to take some more time, right? The circuit needs to come up. The VPN tunnel needs to establish. Our BGP routes our BGP peers need to actually peer and share routes. So we can show that up here. So right now we have 0 prefixes received. Takes about 26 seconds or so. And there we go. We have all our prefixes received, and we can see that things have converged, and we're back over overlay 1. So that satisfies test number 4. Test number 5, let's talk about, actually, let's keep this going. Let's talk about application steering. So let's look at our SD-WAN configuration, our SD-WAN rules. We have a single rule right now that basically prefers overlay 1. Let's say we wanted to create an application steering rule. let's say we had a web server at the data center, or some sort of application at the data center that we want to make sure takes the best path, the lowest latency, lowest jitter, lowest packet loss path. Or let's say we have an application steering rule that actually is out toward the internet. If we have something out toward the internet, we can make a rule for, let's say, Microsoft, for Microsoft Azure. We can use an internet service right here. Internet service is basically a database of IP addresses and services that Fortinet FortiGuard keeps for us. It has a very large amount of entries for any one of these services. The other way we can do application steering is based on application, where it actually looks at the application signature. So we can look at Office, let's see, Microsoft Office 365. We can put that in there. And Office 365 is, across different protocols, TCP, HTTPS, SSL. And it does application inspection to look at the application that's traversing the FortiGate to do this application steering. Obviously, in this scenario, we're doing just VPN traffic toward the hub. So let's actually create an application steering rule for the actual individual host 1.1.1.1. We're actually going to specify just ICMP, and the sources for all traffic. And we actually want to use the best quality link. And if there's a tie, we just want to use the overlay 1 first. The SLA we're going to measure is toward the hub, and we're looking at latency. So we build that rule out. Obviously, the rule goes into position number 2. We're going to slide that up to the top position. And let's see what's happening here. So if we look at our performance SLAs, everything is in SLA, and overlay 1 is the best path, right? It has a sub 1 millisecond latency. Overlay 2 has 22 milliseconds. So if you remember again, the hub itself has a performance SLA of 120 milliseconds. If it falls out of that 120 milliseconds, it will take the secondary path. What we're going to do here is actually not make it fall out of latency. We're just going to make the latency slightly higher, but below that 120 milliseconds. So let's do 44, which should bump us up to 88 milliseconds round trip. Now, if we look at our performance SLA, we are still within SLA, but since we have that application steering rule, you can see it take effect right here. If we have the application steering rule, the application steering rule looks at this and says, hey, we're within SLA, but overlay 2 is less milliseconds. It's actually better quality than overlay 1. So we're going to flip over to that, specifically only for that application rule. So if you look at our application steering rule, we're using overlay 2 because it has the lower latency. But then for all of our other traffic, since we're within the SLA, we're using overlay 1. That is the Fortinet SD-WAN ADVPN in a nutshell, with pretty much all the scenarios that I can think of that satisfy most customer needs. Thank you.